Good afternoon, everyone. It's a special pleasure for me to be here. I've been many times in Leuven, but as you can see, well, I don't know why the first line is not appearing, but it is there. So what I would like to share with you, I was really delighted to see many points. I'm an engineer, real engineer. My background is microelectronics. Although in last 12 years I am heading the faculty or the Department of Information Technologies, so more into computer science. And as Jos mentioned, I also have, I'm wearing another hat, being involved in this huge professional organization which is called the Institute of Electrical and Electronic Engineers, which is worldwide 430,000 people. So the membership is really big. Around 60% is outside the US. The history is started in the US, but we are worldwide. And we are also covering recently, we are engineers by background, mostly. But in recent years, we also have a society for social implications of technology. So we really develop in many different domains. And I will show you a short overview of microelectronics, which is obviously my kind of hobby, a part of being a daily job. And we'll show you what I call the revolution, or evolution, if someone prefers to call it this way. We came, or to the point where we are being now. So everyone probably has a laptop or an iPad, or everyone has a cell phone in your pocket, and probably you don't realize what is inside. So I will tell you a few words what is inside, but then I will tell you a few warning signs from another side, which for a long time was not really looked into, but we are more and more conscious and more cautious as well. Okay. So as you can see, is the electronics omnipotent? Well, we all have these devices. What can we do about it? Can they be useful or not? Okay. So first of all, technology perspective. So if you look at the area of electronics, well, those devices, I just put a few examples. In 1912, so beginning of 20th century, we had this big vacuum tubes, and over the years they were shrinking, getting smaller. Then came the invention of a transistor. Then we have the first integrated chip here. It's very recent, 1958, and it had 5 transistors inside. And now we have in the year 2000 we crossed the number of transistors in the chip, 42 million, and God knows where we are heading. So just to show you, these are the first integrated circuits. Pretty funny now looking at it. It seems obvious that it should be possible to integrate something like this. It's not so obvious how you integrate millions of those, how you can shrink them. As you can see, Jack Kilby got a Nobel Prize. He was Nobel Prizes in physics, but it has many links with electronics as well. Okay, so an interesting, thoughtful thinking is due to Gordon Moore. Gordon Moore is one of the founders of Intel. So probably all of you know about the company Intel that is fabricating the microprocessors and many other electronic things. So Gordon Moore predicted that the number of transistors on a chip will double every 18 months. And this prediction continues for a long time. So this is how we got into millions over the years. But at the same time, so in '65 he wrote this paper about cramming more components onto integrated circuits. But at the same time, he noticed that design is taking much more time, especially testing. So if we design something more complicated, verifying that the design is really useful and serving the purpose is growing exponentially. So this is almost linear, this is exponential. Okay, so now we are getting into everything is going to the nanoscale. So just to bring your attention, so we are going to the scale of a single atoms. Okay? So football, 22 centimeters diameter. Here we have 0.7, 10 power minus 9. Okay. What is nanoelectronics? So we are trying to operate on the nanoscale. So in this very tiny distances, and actually if you think about it, so the hair is around 10 micron. So our hair is very big comparing to what we are able to build. A blood cell is around 2,500 nanometers. Just to show you some comparison. So we are trying to do the engineering on the scale which is obviously invisible with our eyes. And industry is really doing it. So this is happening. So we are below, well, in the scale of nanometers here, okay? And also cramming billions of transistors. I have some examples. So if you are interested, if you have an Apple iPhone, you can see this. There are some Apple A8. So they are built into your iPhones. 2 billion transistors inside. This is just the processor. So can you imagine what is sitting inside in your chip? And some of the most complicated ones, as you can see, maybe some of you are using also, so the FPGA, field programmable gate arrays, the kind of universal circuitry that is being used, they go into 20 billion now. Okay? So this is what really the progress. From 5 transistors, we are going to 20 billion. Pretty amazing. So for an engineer, this is an area which is truly fantastic, amazing. We feel like, well, magicians in a way. My first computer that I still have in my, well, one of my shelves, had an 8086 processor. So it had around, well, this is not the same, but it had around 2,000 transistors. In 2014, when I prepared this slide, it was 2,600,000. So the ratio in between the 70s and then the year 2014, the ratio is over 1 million. 1 million times more squeezed inside. The speed also raised, and the area of the chip and other things. We are almost approaching the limits. So if you think about it, most of these devices are built in silicon, but the distance of the silicon atoms is 3.12 angstroms, 3.12 nanometer. So we're heading towards technologies in the 7, 10 nanometer range, but the distances of the atoms are 3. Can we go much further? Very difficult. So I found 2 amusing pictures. So these were my students' times, and this is what we have now. So actually, the machinery that we use for measurements, there are atomic microscopes, scanning microscopes. These devices are, worth millions. An oscilloscope was a simple thing. Probably, well, no problem buying one. These devices are not for everyone. It's really expensive equipment, very sensitive, very difficult to operate. So everything is changing here. Okay. So we are approaching the limits of current technologies. So if the chips are getting too big, they are difficult. So the production yield, as we say, so the economic side is getting into it, because only very small percentage of the fabricated devices are really functional, if it's very big. Okay, so we cannot build them bigger because they will be very expensive. Well, the size of the feature on the chip is getting smaller, so it's also difficult. And obviously, there are other problems, technological problems. I don't want to bore you with those, because for a non-specialist, they're maybe not so important. There are several organizations that are looking into the future, trying to tell us how this sector will develop. And one of the organizations is called ITRs. It's a consortium of companies fabricating devices, integrated circuits. So those companies are getting together and they are trying to foresee what will be happening in the future. Actually, the last report they made in 2013, and it seems that they stopped. They are not really doing anything more. But this last technology roadmap clearly is showing two things. So one, this is the standard, well, Moore's law, okay? So the number of transistors is growing because the size of the feature of the individual transistor is smaller. But people are also looking at other technologies. So other technologies are equally important because we expect that, well, skip that, press the wrong button. As you can see, there are also electromechanical parts, there are chemical parts being built into circuitry. We build laboratories on chip. We have fluidics, we have whatever you imagine that you can integrate into a circuit or together with the circuit is coming into the picture. Okay, so this is from last year. As you can see, already the Horizon 2020 was mentioned. So the Horizon 2020 is also looking at the technology content. I was sitting on two panels in Brussels, actually. One is called System Integration Panel. So we are really considering what will be happening and which is new in this picture. As you can see, we have here more, so development of what was on the ITRs. We have more than more, so these new technologies, but they called it, here you have something they call much more than more. Okay? So, and what is meant there is, we call it heterogeneous integration. So integrating various parts on a chip that come from completely disjoint technologies. Different ways of putting things together. So far, there are some successes in it, not so spectacular. Some already on the industrial level. As you can see also on this technology content, we also have plastic electronics, organic electronics, so completely new ideas. Abrupt change in technological side as well. Okay, so some of the examples that are really working already in this direction, we have hybrid memory cube concept. Again, here the companies are getting together. The investment, the initial investment is too high for a single company to maintain. Huge companies. Memory producers from Taiwan, from US, Japan, Korea, they're coming together to build a new concept, new idea. Another example, this is also working, as you can see, completely new technologies. Chips are integrated in layers in three-dimensional structures. So very new idea, already working. So basically what we are looking at recently is fabricating something we call a system on a chip. So before we had a whole, for example, radio or another apparatus that was built on a printed circuit board, different parts. Now we are trying to squeeze it into one single chip. You can see many companies are also making outlooks into the future. So we have EU technology roadmap. As you can see, we have the standard transistors, CMOS, so the silicon technology, but together with spin devices, we have optical modulators, whatever comes to your mind, which is an electronic circuit, people are trying to squeeze together. This is another idea from IBM. As you can see, we have a processor layer, the memory layer, and interconnects are made in an optical way. So again, heterogeneous integration. Okay, so further development goes into 3 dimensions. We can put also sensors here, chemical and biosensors, other sensors, image sensors, microelectromechanical devices, converters, memories, whatever you want. Batteries, we are also putting batteries now. So the systems become completely independent. New materials apart from silicon, heterogeneity seems to be the key for the future developments. Okay, now, so if you think about applications, this is also important because next I would like to say a few words about societal implications, how this affects our environment, our life, and how we live. You have to realize that these devices are coming into many domains. So we have fantastic developments, technological developments that are used in a variety of applications. So computers or telephones are just one area which I mentioned already, but we have also medical devices, so laboratories on chip. For example, if you do the DNA testing, basically this is done using a single-use chip, which is worth $20, so relatively cheap. Before it was, really very, very expensive kind of examination. Now it's done almost automatically, on chip. So we have a variety of sensors. Sensors is something that in recent years made a fantastic career. We have, if you have a lift or escalator, we have velocity sensor, we have acceleration sensors, we have them in the cars. Well, you have GPS, another example, in the cars, in the cell phone, they're being built everywhere. So these microelectronic chips are really almost everywhere. You mentioned in your talk those meters that are being built. I will mention a little bit about the Internet of Things, because the core of Internet of Things are sensors. Okay, so there are many demands in it. So as you can see, high speed, increased battery lifetime. So all these devices depend on batteries. So this is another area which I will not be able to talk about, but batteries are extremely important. We need more data storage, so memories, bigger memories, multifunctionality. So we want to have everything in the cell phone, for example. And everything has to be packaged in one. So as you can see, we have human applications, human plus, biomed and life sciences, radio, low power, imaging, sensor systems, energy systems, and all together, it covers these new areas of electronics. Okay. Just 2 slides about new materials, because probably you've heard some of the developments as well. So new materials like graphene is coming into the picture, and we are expecting that this will bring another revolution, but not yet. Laboratory developments are there, but real applications, not yet. Okay, so this is a beautiful picture. From the technological side, you see really a beauty, an amazing development, fantastic new technologies. So people were announcing the end of like silicon technology years ago. Still there, still better, still faster, more compressed, more things on chips. God knows where are the limits. This is from a technological point of view, this is really a spectacular development. Unfortunately, there are many bad sides that are coming with it. And you will discover also that, you know, being an engineer, I come to many same concepts that were mentioned in the previous talk, seen from a very different perspective. So I can, first of all, I can say, unfortunately, not everything is so beautiful. Okay? And what is not so beautiful is the perception from the societal point of view. Okay, so everyone nowadays is aware that we have electronic waste. So we are producing new generations of this apparatus. What happens with the old ones? So basically the survival of a laptop or a telephone is a couple of years, 3 years. If someone is really dedicated, maybe 5 years. What happens later? You just dump them, okay? Or they are taken somewhere, we don't know where. It disappears from our picture. The reality is that majority of these devices are just taken away from our site. They are taken to Ghana or to China and dumped. And in many cases, they are disassembled because they contain many precious metals, many precious materials. So parts of it are worth some money. And they are, well, probably you hear also reports about child labor in China being used to disassemble them. One thing which is improving over the last few years is that the designers are taking into account the possibility of disassembling things. If you look at the first models of iPhone, they were just one single block. To remove parts that are valuable, you had to really take a hammer and knock it into pieces and then extract what is valuable from inside. And mainly this was done by children, by Chinese children. In Ghana, you can see on YouTube, you can find movies showing mountains of computers, cell phones, other electronic devices, whatever you imagine. This is a big problem. Obviously, we are trying to solve it. I don't know, maybe some of you could hear the talk of the president of Umicore, the company. We had him, I don't remember the name. Egbert Locks, yes. We had him on one of our symposia that we organized with yours. There are spectacular things that are happening. So there are companies who are taking care. Instead of dumping it in Ghana, it goes to a company that is fragmenting it, processing and recovering gold, platinum, whatever. So this is one very, very bad side which is clearly visible. Small things are happening on the good side to improve it. When you disassemble those things, you also have to realize that there are very, very nasty materials inside. Apart from those that are precious and worth to be extracted, they are very poisonous things. And there is a whole list. Actually, ITRs also defines a whole range of restricted materials. They are poisonous, simply poisonous. If you disassemble your iPhone, you have a big risk that you will sniff something which is very bad for your health. Okay? So they are hazardous wastes, they are volatile organic compounds, but we also have to realize that the production involves usage of huge amounts of water. So this is 7.8 liters of water per centimeter square of a produced chip. Consider billions of chips that are produced for all your computers, all the equipment that we are using. This is really water-consuming industry. If you just think about how beautiful things we can do with the devices, that's fantastic, but the expense is really very, very large. If we realize that there are big areas on Earth that suffer from shortage of water. And obviously also energy, so consumption of energy is pretty big also. Actually, if you could see the factory producing chips, they are really huge buildings like those producing Airbus airplanes. They are producing these tiny things, but the buildings are amazingly big, which relates also to the whole machinery consuming water and energy inside. Okay. So recycling is good, but can we continue using these technologies? And the second question, because if we expand these technologies, we will be using even more water and even more energy. Can we pay for it? But for me, from my point of view, and this is also one of the questions that we are asking ourselves in our Association of Engineers, is who is really taking advantage of all these results? Because, well, we are really privileged people being here, having all these devices, having all this equipment. Those little kids that I was showing, disassembling the electronic devices, electronic parts, they never use them. They are not for majority of people on Earth. So there is a very big disparity here. Obviously, I don't know whether their happiness will be bigger if they will be given a telephone. That's a good question. Okay, and but still, well, we have to realize that we are a very small group of people taking advantage of all these developments. I have to be faster.
5 minutes.
Okay. Well, the notion of smart was already there, but with this electronic development, we are trying to make everything smart. We are talking about smart homes, smart cities. So homes are equipped with millions of sensors, temperature sensors, humidity sensors, gas sensors, whatever. In the refrigerator, in the cooker, I don't know, in the bathroom, and closing your windows, whatever, everywhere. This is easy because we have those technologies, and they are becoming cheaper also with the development. But you have to realize, some people are saying, Big Brother is present. This was also mentioned in your talk. If someone would like to watch what you are doing, he can sense it. You have all the sensors, they're measuring what you are doing, how you are moving around the house, in which room you are, and obviously what kind of movies you are watching, but also more delicate questions. Everything can be detected. So on one hand, we have destruction of environment, chemical and electromagnetic hazards. We have loss of privacy, big security issues, and also we have to realize that we are getting robots everywhere. That's another question which remains without answer and is becoming more and more interesting. Okay. In our Association of Engineers, we were for a long time talking about humanitarian technologies, and now we start talking about human-centric technologies. Humanitarian was just trying to help people in, undeveloped or unprivileged areas of the world, while human-centric is going towards everyone. Okay? And ending my presentation, I would like to I prepared a couple of slides about two approaches to the future which are visible among different nations. And obviously governments are trying to predict where to go in the next 5-10 years. And there are two trends. So one trend is called Industry 5.0, improving, make industry more tolerable by everyone on one hand, and also bringing it nearer to the people. And recently, I was 2 weeks ago in Japan. I had an opportunity to meet with the government level official, the director of the Technology and Innovation Agency, Dr. Kuma, and they are taking quite different approach. They call it Society 5.0. So if you talk to German people in Germany, they will talk about Industry 5.0. The Japanese are talking about Society 5.0. Okay, so in Germany there was a big program that there was a group of scientists that produced a report in 2013. You can see it here, recommendations for implementing the strategic initiative Industry 4.0. Okay? There was a working group, 2013 they produced a report. As you can see, this is the evolution, so this was the 1.0, 2.0, 3.0, and this is 4.0. Cyberphysical Systems. Cyberphysical Systems basically have four special features. They offer interoperability, they offer information transparency, they offer technical assistance, and they also are characterized by decentralized decisions. So these are the four main points behind the 4.0. What is 5.0 then? Because this seems to like a status quo. What we have now is really developed. So 5.0 tries to bring the interaction between what is robotized completely again with the humans. So robots working together with people. So not only for people, but together with people. So we were trying to build production lines that contain only robots. Well, I don't know, 500 robots in a big building, one supervisor just in case something goes wrong. Now they're working together, hand by hand. No more robots that are surrounded by fences. They are together with people and safe for people also. Okay. Basically, 4.0 was meaning losing jobs because humans were replaced. Okay. And 5.0, we are working with intelligent robots capable of working together. So last two slides. What is the Japanese perception? So as you can see here, this is the definition from their official governmental document. What is society 5.0? It's a society that can be expected to facilitate human prosperity. Such a society is capable of providing the necessary goods and services to the people who need them at the required time and in just the right amount. Is able to respond precisely to a wide variety of societal needs. Society in which all kinds of people can readily obtain high quality services, overcome differences in age, gender, region, language, and live vigorous and comfortable lives. The Japanese society is aging. If you talk to the people there, average age is getting higher and higher. They need more assistance for older people. They are pretty different. The society has different structure and different needs, different ideas also. So they are trying to address not only the questions of producing more interesting goods, but trying to start from the beginning to see where there is a need to improvement. But this is a government plan. Obviously, it's elaborated on many pages later, but these are just the main points. But I thought I would bring these 2 slides to you at the end of my talk, just to show you that there are people who are taking very different approaches. That on the governmental level, the thinking is not separated for engineers, social scientists, whoever, medical doctors. From the beginning, on the decision level where we are funding research, we are funding projects, it starts from the society. Okay, so this is my last slide. It gives you a little bit more details of what is inside this program. As said, you know, these documents are available, so if you're really interested, you can find them on the internet as well, I believe, in English. Not everything is in Japanese. So thank you very much for your attention.